Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. This is the third in a series of short videos on basic electronic circuit analysis. In the first video, I covered Ohm's law. In the second video, I covered the first of Kirchhoff's law, Kirchhoff's current law, or KCL. In this third video, I'm going to cover the second of Kirchhoff's laws, Kirchhoff's Voltage Law, or KVL. If you find this video helpful, please click on like and subscribe so that you'll be notified when new videos come out. Now, this law was named after Gustav Kirchhoff, a 19th century Russian-born German physicist. Kirchhoff's Voltage Law, or KVL, was announced in 1865 along with his first law. It states that the algebraic sum of the voltages around any closed loop must be equal to zero. Well, what does that mean? Well, let's take a quick look at this on the whiteboard to find out. Well, the first question we have to ask is, what is a closed loop? Remember, it says that the algebraic sum of all voltages around a closed loop is equal to zero. Well, a closed loop is a circuit where you can start at one point and then move around the circuit from component to component and able to end up at the same point that you started out in. The key to understand what this means is setting a reference for what constitutes a positive voltage and establishing a direction of travel around the loop. If we consider a circuit and travel clockwise around the loop, as we move from one point to the next, the voltage goes from a less positive level to a more positive level, then we say that the voltage is positive. If, as we're traveling around clockwise, we're going from a more positive level to a less positive level, then we say that the voltage across that component is negatively. So let's consider the most simple of loops here. We have a battery and a resistor. And let's just say we have point A and point B. This is the positive side of the battery, this is the negative side of the battery. So let's say we're starting at point B. This is VB. And this is R resistor, and the equivalent over here, the voltage across this resistor is V sub R, okay? So that's the voltage across the resistor. This is the voltage across the battery. Now, as we move from point B, and it's arbitrary, by the way, what direction you choose to go and how you choose to establish this. But as you're moving around here from point B to point A through the battery, you're going from the negative side of the battery to the positive side of the battery. Therefore, VB is going to be some positive value. All right, so we've gotten to point A. We're going to continue moving around this closed loop. See, we've gotten back to the same place that we started, so it's a closed loop. And now we're moving from point A through the resistor to point B. Well, point A is the positive side of the battery. We've moved through the resistor. We've come back to where we're started, to the negative side of the battery. The voltage across this resistor has gone from a more positive value to a less positive value. Therefore, the voltage across the resistor is going to be defined as a negative voltage. So VB plus VR must equal 0. And because VR is negative, this comes out VB minus VR is equal to 0. And in this case, you can see that VB and VR have to be the same value. All right, so let's consider a situation here where we have more than just these two components. So now we're going to move through a resistor here, through a resistor here, come back to a resistor here. We have point A, we have point B, we have point C, we have point D. Now, arbitrarily we choose to start at point D, and as we're moving through the battery, we're going from the negative side to the positive side, so the voltage across the battery is going to be positive. Now, we've already established that if we had a resistor here, the voltage across that resistance is negative, but now we have 3 resistors out here instead. Well, it's the same deal. As we're going from here, the positive side of the battery, toward B, through R1, the voltage is going to be going down because we're traveling through this toward the negative side. So VR1 is going to have to be negative. And here we are, VR2. Again, we're traveling from B to C around this closed loop, and we're going toward the negative side of the battery again, so VR2 is also going to be negative. And R3, the same thing as we travel around here. This is also going to be negative because we're going from a more positive point to a less positive point. And so let's just say that the voltage of the battery is 10 volts. The voltage across R1, we measured that, is 3 volts. The voltage across R2 is 5 volts. What is the voltage across R3? Well, Kirchhoffs voltage law says VB plus VR1 plus VR2 plus VR3 equals 0. So 10 plus our minus 3 volts plus our minus 5 volts plus VR3 is equal to 0. Well, this whole section here is equivalent to 10 minus 3 minus 5. And 10 minus 3 is 7, minus 5 is 2. So 10, or 2, plus VR3 is equal to 0. Subtract 2 from both sides, and you get 0 here, so you end up with VR3 is equal to minus 2 volts. That's Kirchhoff's voltage law. Now, just as a point of note, that this law applies, consider this situation where you have a battery, a resistor, a resistor, a resistor. We've seen that already. But what if we have something out here too? Kirchhoff's voltage law can be applied around this closed loop and this closed loop. It can be applied, it applies to any closed loop in the circuit. So, Kirchhoff's voltage law. So there you have the short and sweet of Kirchhoff's second law, also known as Kirchhoff's voltage law, or KVL. It is the third law. There's Ohm's law, Kirchhoff's current law, and now Kirchhoff's voltage law, which is the undercurrent beneath all circuit analysis. In the next video, we'll be talking about Thevenin's theorem. If you found this video helpful, be sure to click on like and subscribe to this channel. In the meanwhile, thank you so much for watching. Toodaloots.